Hello, ladies and gentlemen. My name is Mariam Bahrami-Pana. I am the chair of IEEE Central Montana section. So on behalf of IEEE Central Montana section, I would like to welcome you to this webinar. And it is a great pleasure for me to introduce our speaker today, Mr. David Dolezilek, who is the International Technical Director of Schweitzer Engineering Laboratory, SEL. David has been involved in product development and in the design and application of solutions for complex power system challenges around the world for over 30 years. So he's Montana State University alumni, and he has been a strong contributor to many IEEE, SIGRE, and IEC standards related to digital communications and cybersecurity. So David has several patents related to the control circuits, communications, and security, led the development of the first Ethernet interface designed for mission-critical control systems, and he popularized the term OT to describe the use of operational technology communications among intelligent devices. Today, he's talking about the engineering challenges affecting the safety of modernization of energy delivery system. David has collaborated closely with another Montana State University alumni, Alan McDonald, who sadly passed away on March 2021. Now I'm going to give the floor to Dave so that he can elaborate on the anticipating and avoiding hidden failures in communication-assisted protection. David, floor is yours.
Thank you very much. Can you hear me okay?
Yes, perfectly.
Great. Thank you for this opportunity. And yes, so this paper is specifically about our observations in using digital communications among control circuits for protection systems, but it applies equally to any industrial control system. I wanted to start with a few acronyms and then observations, and then I actually made a video of the presentation because I wanted to show some equipment, so I'll be here to answer questions afterwards for sure. But I wanted to start with the acronyms. So here you see EDS, which is an energy delivery system. So today I'm predominantly talking about electrical energy, and this chart shows the reason why we're concerned even before we digitize the traditional hardwired circuits in a control system of an energy delivery system. We have the challenge that most of the most of the misoperations are either human error or equipment being inappropriately used in the control circuit. You can see 30% of the errors are due to people making mistakes in logic or settings in the devices, and 13% are communications failures, and 19% are inadequate equipment for the harsh environment of the electric power system. So we know from some surveys that roughly 56-60% of North American utilities are considering moving toward digital control circuits and digital communications. And so we're concerned that that be done correctly. And we make the observation that OT people don't presume they know how to do IT, but the opposite isn't true. So I don't intend to cause any offense, but this presentation is built on observations we've made where IT people perhaps mistakenly feel they're prepared for the design and application of communications and OT systems. And so we want to raise the concern that we should have a healthy dialogue before we enter into some control circuit challenges or that they become a problem in the field. So EDS is energy delivery system, ECS is energy control system, IED is intelligent electronic device, which is a specialized piece of hardware with a computing platform that does automatic and logic-based decision-making in the field. With that, again, the presentation isn't intended to cause offense. It's just a sharp reality check of what's happening in the marketplace. So next I'll play the video I mentioned, and then we can have a dialogue afterwards. Hi, I'm Dave Dolezilek, Principal Engineer with Schweitzer Engineering Laboratories. And the first thing I'd like to do is thank my co-authors for their work on this paper. My daughter Anna works for a large global software company to certify users' capabilities before they accept important assignments where they use those software tools. And Alan McDonald was a fellow Montana State University alumni who recently passed away. And he and I collaborated on topics like this for many years. Alan was an aerospace consultant, lecturer, and author, but in his earlier career, he was the director of the Space Shuttle Solid Rocket Motor Project when the Shuttle Challenger exploded. In his book, Truth, Lies, and O-Rings Inside the Space Shuttle Challenger Disaster, he explained that he'd been concerned about the below freezing temperatures and that they might impact the rocket's O-rings for the Challenger launch. He summarized. I'm sorry. Hi, I'm Dave Dolezilek, Principal Engineer with Schweitzer Engineering Laboratories. And the first thing I'd like to do is thank my co-authors for their work on this paper. My daughter Anna works for a large global software company to certify users' capabilities before they accept important assignments where they use those software tools. And Alan McDonald was a fellow Montana State University alumni who recently passed away. And he and I collaborated on topics like this for many years. Alan was an aerospace consultant, lecturer, and author, but in his earlier career, he was the director of the Space Shuttle Solid Rocket Motor Project when the Shuttle Challenger exploded. In his book, Truth, Lies, and O-Rings Inside the Space Shuttle Challenger Disaster, he explained that he'd been concerned about the below freezing temperatures and that they might impact the rocket's O-rings for the Challenger launch. He summarized our paper with this quote: "As engineers, it is our job to understand and mitigate potential failures. We pursue quality, but cannot prove its absence." His team was tasked to evaluate and mitigate vulnerabilities, but ice in Florida had been an unlikely or low probability event and was not studied. His team was accountable for the launch decision, and they said that based on all available evidence, the system conditions were far outside the safety margin. And here you can in fact see a photo that Alan provided that shows the ice on that morning on the launch pad. The engineers explained that there was no test data or evidence that a launch would be successful below 53 degrees Fahrenheit, and all the engineers voted against the launch. Management really wanted the launch to proceed and challenged them, "Can you prove that the launch will fail?" At which point Alan said, "That's not how engineering works. All of our tests show when success is most likely, and that data cannot be used to prove the opposite." So management overrode the engineering and they authorized the launch. 73 seconds into its flight, Challenger broke up, resulting in the deaths of Francis, Michael, Ronald, Ellison, Judith, Gregory, and the teacher Krista McCullough. When visible and known vulnerabilities are dismissed by individuals unprepared for the role of mission-critical design assessment, unintended consequences result in hidden failures that reduce availability, reliability, and dependability. Alan shares that we must address known knowns, known unknowns, and unknown unknowns. Known knowns are the most prevalent areas of concern and are most likely to cause a failure. The O-ring system had numerous known knowns that the engineers were already concerned about. Known unknowns will eventually cause a failure, but there's not enough data or evidence to know where that failure point is. This is the exact reason why the Morton Thiokol engineers recommended not launching the Challenger in temperatures below 53 degrees. And unknown unknowns are conditions that were never even considered to happen, such as the cause of the disaster: gaseous oxygen vapors leaking from an external tank led to an explosion at throttle up. Allen later explained to the Presidential Commission on the Disaster that his engineering team had voted not to authorize the launch. The chairman asked Allen's boss, "Have you ever had another experience where all the engineers voted one way and management voted the other?" And he refused to reply. Afterwards, Allen said, "I decided what's better than thinking about would have, could have been, is to make sure it never happens again." Allen and his team created improvements that led to 110 more successful shuttle missions with perfect boosters. And Allen told me that shuttle astronauts told him that they felt the boosters had become the safest piece of equipment on the shuttle. Problems happen when people feel compelled to follow social norms and not contradict a person with authority. People often assume that an author or a speaker is sharing facts, and this, of course, is a problem when the speaker is wrong. For example, the IEEE Code of Ethics illustrates the error made by operators at Chernobyl when they bypassed protection systems to avoid a confrontation with their boss, in direct conflict with the established company safety procedures. Failures such as this further emphasize the engineer's obligation to protect public safety. So how does this happen? In his research, Professor of Psychology David Dunning has shown that some people tend to believe they are right without any evidence. He describes that many people are unskilled in a specific area and are not only unaware of their lack of real skill, but they're absolutely confident that they are right without any proof. While people that know about the topic are far less confident that they know everything and they want to test solutions. Unskilled people often rely on social truth rather than scientific truth. They reference a document such as a standard or a magazine rather than learning from performing simple experiments. The social proof is the same reasoning used by people that believe in the supernatural and karma and miracles. However, engineers need to insist on scientific proof and evidence and not superstition. This is becoming a difficult challenge from IT professionals that simply do not understand control circuits and operational technology, or OT. Dunning suggests that IT specialists are often overconfident in working in OT because of their perceived success with Ethernet and business systems. Accidental success of an IT process during an Ethernet failure are falsely considered evidence for their use in OT systems. Ethernet specialists need to realize that they are accountable to understand the consequences of their choices and their role in the safe operation of OT in systems like aviation, healthcare, and energy power systems. While greed drove this fictional IT villain to accidentally trigger a cascading failure in the movie Jurassic Park, real-world cascading blackouts are often triggered by a single, simple failure, often the result of the use of inappropriate technology or design by people unaware of the possible outcomes. The Electric Reliability Organization recommends consequence-informed planning and operation, as well as resilient system design for energy control systems. Once again, with the Columbia, well-documented failure modes were hidden in plain sight. Foam breaking off and striking the orbiter was a frequent launch event. These earlier near-miss failures created a false sense of confidence rather than alarm, and they gradually became viewed as normal flight risk. After a large foam strike in 2003, NASA managers chose to reject the option of repair or rescue and proceeded with the Columbia landing as planned. And on the morning of February 1st, the Columbia disintegrated at 18 times the speed of sound. During failure analysis, while the Columbia was still in orbit, Boeing engineers chose this slide to share their findings. This literally led to death by PowerPoint. The title is confusing and there's far too many words on the slide. and the necessary life-saving information was hidden in plain sight way at the bottom of the slide. And in fact, what it should have said is the fact this foam strike during launch was 600 times larger than any previously tested damage. We don't have any evidence that it will survive re-entry. Instead, we lost Rick, William, Ian, Kaplana, David, Laurel, and Michael Anderson from right here in Spokane, Washington. Alan said that the Space Shuttle Columbia is a good, bad example, illustrating the deadly consequences of incorrect risk assessment when faced with a witnessed known failure condition. A post-disaster study determined that had NASA evaluated the foam strike as advised, either a repair or a rescue would likely have been successful. Safely adopting new technology represents a positive change that will expand the knowledge of engineers and technicians as they learn new skills. However, along with innovation, preoccupation with failure is not bad. Highly skilled professionals are continuously vigilant for opportunities to prevent even small failures from becoming catastrophic failure. We must apply critical thought to identify and mitigate unintended consequences resulting from these hidden failures and vulnerabilities. The National Electric Reliability Corporation, NERC, fault avoidance and fault tolerance requirements include avoiding an outage after the loss of a single component as N-1, continued performance after the loss of two components consecutively, N-1-1, and continued performance after the loss of two components simultaneously as N-2. For example, consider the typical ISA and Purdue model of a control system where the physical level is the process at the bottom. This level 0, in this case, is the process of generating and delivering electric power. In other examples, it might be a surgical theater or aircraft control system. Above that, we have the safety and protection system. Above that, automation. Above that, access to other substations and control centers. Above that, the supervisory control and data acquisition. And then the electronic perimeter where communications change from OT, operational technology communications with machines, to IT on its way to level 6, which is the people. So for this paper, we discussed the OT communications of the substation called station bus, and more specifically, the OT communications within the process called process bus communications, such as the critical control circuits like the digital trip circuit to operate a breaker. Here we can see the purpose of a correctly operating trip circuit on the right. The control circuit can't prevent the fault, but as soon as we detect it and trip the circuit breaker, we can stop the flow of electrical energy into the fault. You can see that the energy fed into the fault on the right is much less, and we are better able to protect people and equipment. This test was done with a digital trip circuit. The relay opens the breaker to stop the flow of energy into the fault when it gets a trip message from the device that detects the fault. And in this case, that trip command travels as an Ethernet message through an OT Ethernet network to trip the breaker. I recall being impressed during my last advisory board visit to Montana State University when a student explained his fault tolerance design for a satellite project, because fault avoidance is a hope but not a plan, and certainly in space. The IEEE fault avoidance and tolerance design considerations for the present definition of a hardwired trip circuit, shown in blue, that are directly wired to the sensors and actuators in the process, include concerns about temperature, wind, ice, rain, snow, electrical storms, humidity, altitude, and earthquakes. And the communication channel in this example is for station bus communications, including what IT would call data at rest, things like settings in the relay, and data on demand, like read-only metering of power flow or read and write access for control commands. Process bus communications are machine-to-machine protocols like mirrored bits communications and Ethernet messages such as generic object-oriented substation event, GOOS, sampled values, and precision time protocol. As the protection system definition evolves to this digital trip circuit, we need to add additional power supplies, process bus connections to digital relays, new merging units that digitize the wired connections to the process into from analog to digital messages, clocks, Ethernet switches, which all increases the cyber threats and fault considerations. And here we are adding communications completely unfamiliar to IT staff. This is data in motion. Machine-to-machine messages critical to control, such as currents and voltages and trip signals. For example, some trip circuits require that an Ethernet network fault be detected and corrected in less than 417 microseconds. Metrics for product reliability include the failure rate and mean time between failure. For example, if you were considering choosing to buy an electric bicycle, you might compare the ones available based on the miles to failure if you were concerned about reliability. Or if you wanted to compare desktop computers and IT Ethernet switches, you would look at time to failure based on their use 6 hours a day, 5 days a week. However, control circuit devices must be measured on failure rate based on constant use all day, every day, 24/7. We need to understand the quality of the different methods to exchange protection signals. So for hardwired I/O, we need to understand and preserve the operation of the physical contacts. So we need to understand shock and vibration, humidity, temperature, thermal expansion, all the things that cause wear and stress and corrosion on the contacts and affect the reliability. For serial communications and Ethernet digital message interfaces, we have to worry about connectors, microcontrollers, transceivers, and oscillators. SEL knows every device we've ever built, who bought it, and we've found root cause of every known failure. And we've used that information to improve our products and improve power systems. Answers from SEL data scientists gave me availability evidence for thousands of these relays installed around the world. So for example, looking at this relay platform, we can see we have contact I/O on the back used for wiring copper wires to the actuators and sensors in the process hundreds of yards away. The reliability of this card is determined by the failure rate in service. Over the past 10 years, we've had 136, 790 of these boards installed and in service. And over that time, we've had 59 reported failures. Now, many of those, if not most, were actually customer-induced failures where they fused the contacts together by trying to break excessive current, well beyond what's recommended in the instruction manual. However, we don't care. We count all of those failures. And counting those, we come up with an MTBF, or a mean time between failure, of 23,183 years. Now, that doesn't mean that I expect this card to be in service for 23,000 years. What that means is I expect if you have 23,184 of these boards in service for a year, that you can predict that one or fewer of them will fail in service. Here I have the serial interface, RS-232 interface. This board allows me to use digital messaging to replace dozens of copper conductors with messages over serial cables through this communication port. And if I need redundancy, I can add 2 communication cables to do the work. This particular board, this RS-232 board, I've got evidence from 31,906 boards been installed for 10 years. 2 of which failed in service, giving me an MTBF of 159,530 years. Back in 1999, I ran a research and development group that designed this board, the first Ethernet interface card for use in electric power systems or mission critical systems anywhere. The board eventually had a MTBF of 17,000 years, even given the technology we had at the time. It was also designed with deny by default, meaning that all the Ethernet communications that were available were disabled until you engineered the communication network and then turned on individual communications that you wanted. And of course, all the competition and the other devices since then have all the Ethernet enabled by default, which is a real challenge for control systems because we have to hunt down and find all those communications and open Ethernet ports and disable them in the substation. Here we have the fourth generation of the Ethernet card, where we can use a single Ethernet cable to move information, replacing hundreds of copper cables. And this particular board has an MTBF of 32,190 years. Keep in mind, presently we're asked to support up to 30 data on demand connections through this Ethernet cable and up to 142 machine-to-machine data in motion connections, which include the digital trip circuits. Environmental factors can adversely affect the performance and lifespan of equipment. And so at SEL, we design and manufacture our equipment to the highest workmanship standards, same standards used for aerospace and life support. Now, competition and IT devices are normally built to lower standards, the same standards as commercial electronics and toys. So, for example, a common IT Ethernet switch has an instruction manual that says our equipment requires a dry, clean, well-ventilated, and air-conditioned environment. And in fact, if you don't allow a 2-hour warm-up period, if the temperatures get cold, you might damage the internal components. This is a real challenge when people try to use that type of equipment in an energy control system or a substation, and that's why we design ours to minus 45 to plus 90 degrees centigrade. Now, we all know that not only did the cold influence the recent Texas blackout, we also know that 10 years earlier, engineers had recommended corrective actions that were not done. Interestingly, a recent ERCOT report included a quotation by the astronaut Alan Shepard, and I quote, "You say to yourself, okay, why did it happen? Why did we make those bad engineering decisions we made in 1986 with Challenger? I'll tell you, it's the human element. I suggest that there's a complacency there that comes from success." So let's look at the new components of a digital trip circuit. The new components must meet the requirements of the harsh environment among the primary equipment, and these include process bus interfaces on the relay and new merging units, which are direct wired to the process and do the analog to digital conversion. And we need a process bus communications network, and we often need a clock. So let's look at a couple of installation methods. So here we show an American National Standards Institute, ANSI, standardized numeric code 11, where device number 11 is for a multifunction intelligent device that does protection logic and probably other things like reclosing and so forth. The IEEE abbreviations for IMU, or Intelligent Merging Unit, which is a merging unit that does the A to D but also has intelligence like protection logic, or remote IO, which does not have intelligence. At SEL, we build all of these devices, and we build merging units to relay standards for the appropriate availability. In fact, here I have a relay that's truly a specialized computer designed to work 24/7 for up to 30 years and do its job. Considering all the components inside this box, we have a in-service data sharing that we have nearly an 800-year MTBF for the entire device. And we traditionally connect to the process using copper cables that travel thousands of yards from the relay cabinet to the process devices, the breakers and transformers in the physical process level. Instead, we can connect those wires to a merging unit ANSI 11 and then communicate the data between the merging unit and the relay using the digital cables. And this is the simplest connection, direct between the merging unit and the relay. When we need to send data to and from several devices, we use a communication switch. The ANSI number for a communications is a 16, and a 16SS is a serial switch. So here's the SEL version of a 16SS serial switch where we use RS-232 connections so that we can communicate from the merging unit or the relay to the switch, and then from the switch to several other devices. And in this example, this 16SS serial switch is built the same way as our relays, and it has an MTBF of 620 years. And here we see an ANSI 16ES, which is an Ethernet switch. Here's the SEL Ethernet switch. This version has a radiator to dissipate heat, and all the Ethernet connections you might see on an IT switch on the back, but it is very different. It is designed for the OT environment. It's designed and built like a relay, no moving parts, doesn't rely on fans, and it's expected to work 24/7 for 25 to 30 years. Now, from field service information, we know that this particular Ethernet switch has an MTBF of 430 years. Now, industrial and IT switches record their MTBF in hours, not years, and a very popular supplier publishes an MTBF of 29 years for their Ethernet switch, which is 15 times less reliable, even though that data is collected on switches in dust-free and air-conditioned environments. So you can see the disparity in products available that should be chosen and designed into a digital trip circuit. Networks can be unavailable due to component failure, lightning, or other events. However, IT Ethernet creates an entire new suite of failure modes as a byproduct of adding flexibility. These failure modes exist by design and cannot be eliminated. They can only be reduced through sophisticated engineering practices, and they are the biggest culprit hidden in plain sight. And when any of these faults is present, the trip circuit message will not get through and the trip circuit will not function. A challenge to digital trip circuit design exists when designers make the dangerous assumption that IT and process bus communications require the same level of service. Dunning points out that infrastructure support teams such as IT often confuse fit for use. Yes, I understand Ethernet, which might even be fit for the purpose of business operations. They confuse that with, yes, I understand how to use Ethernet for protection as needed on a process bus communications network. Like the shuttle Columbia near-miss foam strike events, near-miss Ethernet faults and the known unknowns about IT Ethernet systems should cause alarm and not overconfidence. Aerospace and aviation control systems historically share a lot of similarities with both the design and the failure of energy control systems. And although the N-2 condition of multiple bird strikes is an unlikely or low probability condition during takeoff, in 2009, when US Airways Flight 1549 struck a flock of geese, they actually experienced a dual primary goose failure. We need to anticipate and avoid dual failures in the process bus as well. Now, back in the day, Social Proof labeled this event the miracle on the Hudson. But scientific proof documents a very well-engineered aircraft, skillfully and patiently navigated by pilots with extensive experience and training who practice great concentration, discipline, critical thinking, and interpersonal communications. It was not a miracle. It was a feat of extreme skill and engineering. Now, the FAA defines failure as a loss of function or a malfunction of a system or part thereof. Each aircraft system failure condition is categorized with respect to the severity based on the prediction of what will happen if the system fails. And the FAA summarizes severity with respect to the impact on passengers, such as minor, it's an inconvenience; major, it's a discomfort to passengers; hazardous is fatal to a small number of passengers; and catastrophic is fatal to all passengers and perhaps the crew. And these severity categories are important. They are used to specify the level of appropriate resilience and redundancy of the aviation system. Now, the Maneuvering Characteristics Augmentation System, or NCAS, was created to compensate for the unusual lift associated with the new 737 MAX engines put onto an old aircraft. Now you can see the engines on the right were moved forward and higher up on the wing. And this MCAS relies on an angle of attack sensor, an AOA sensor, which is actually hidden and not disclosed to the pilots. So putting a new engine on an existing plane meant that pilots did not need to recertify, so there was no expensive classroom or simulator time. And Boeing recommended only 2.5 hours of computer-based training. In the 8 years after the MAX was announced, Boeing's stock quadrupled, profits doubled, annual revenue grew by 50%, and then 343 people died. The fact that the AOA sensor was 6 times less reliable than required for its hazardous rating was hidden. Also hidden was that the MCAS was 4 times more powerful in overriding the pilots than necessary to be classified as hazardous. Both should have been classified as catastrophic, and that would have triggered the appropriate control system resiliency. The 737 MAX illustrates known knowns, known unknowns, and unknown unknowns. But the worst are the false categorizations of known knowns of sensor failure, unexpected lift characteristics, and software override of pilot control hidden in plain sight. The electric power industry categorizes the severity of failures 1 through 5 based on interrupted power delivery. And for category 1, the potential faults include station bus communications. We need to perhaps update the other categories with the larger loss of generation or load to include faults that might result from a process bus communications failure. Perhaps migration to digital trip circuits requires updating the categories. A small fault can cascade into a large outage. We know from surveys that over half of the utilities in the United States are considering moving to digital trip circuits. Back in 2012, 670 million people in India, 10% of the world's population, lost power after a single piece of equipment failed. The blackout in 2003 in Italy was triggered by a single tree. The 1965 New England blackout was triggered by the failure of a single protective relay. And in 2016, about 20 million Kenyans experienced an outage triggered by a monkey. Single, simple failures must be isolated by trip circuits before triggering a chain reaction. But interrupted load is not enough to understand the true severity of failure. The Space Shuttle and 737 MAX illustrate catastrophic failures associated with the inappropriate use of technology and the incorrect categorization of severity of failure. Perhaps we should update categories in energy control systems to include cost in dollars and public safety. An unfortunate example happened in Hurricane Katrina, which provided a real-world example of the need for better metrics. Pendleton Methodist Hospital administration didn't evacuate, even though they knew the hurricane was approaching. The disaster plan managers said they had prepared for a utility blackout and they had bought a backup generator. However, those generators were in the basement and they were quickly flooded, and at least one patient died before they could evacuate. So the hospital actually needed better metrics and a correct severity classification to avoid the failure that was hidden in plain sight. As another example, consider this 345 kV fault that happened in Brazil recently. It also took out an 88 kV line below it, and people could have been seriously hurt. Thank goodness no one was hurt, but it did cause a lot of damage and lost business. This illustrates what happens when a trip circuit fails. So this was a conventional trip circuit, but its failure created a fault duration of an astounding 113 seconds, and the outage time was 376 minutes. But the 177 megawatts of interrupted energy was only considered Category 1 severity. Now, clearly, this was much more dangerous and expensive than the interrupted energy metric would indicate. Dangers to humans are a real challenge. For example, utility workers die in the line of duty twice as often as police officers or firefighters. Electrocution and arc flash are the most frequent private workplace fatalities. And the victims are usually qualified to be where they are working, but they're victims of someone else's design flaws. Digital messaging has a great advantage because we can detect the failure of the reception of a message. And this differentiates between a broken conductor being off or zero versus the lack of reception of the message. And in this example, on the slide, we have the ability in the receiving relay, the transformer relay, to supervise the quality of the information from the feeder relay. Now, when the message fails to arrive, we detect immediately the messaging is broken, and we adapt our logic accordingly. Fault avoidance is a noble goal. However, we need to anticipate a failure and react to it. We need to design fault tolerance into the logic and into the circuits. Fault tolerance first requires that fault detection and then mitigation. As engineers, we do know that dual primary is the most resilient. Here are my dual primary guard dogs, and they're even different enough to avoid several common mode failures. Now, when left to grow long, the hair obscures the Briard's eyesight, and it makes her reactive, and she walks into things, and she's immediately happier when I trim it back. After I inherited the Chihuahua, she lost an eye to glaucoma, and now she has no depth perception. Neither of them could communicate to me their experience. So I use this example to explain the problem with a popular Ethernet replication method of parallel redundancy protocol. For my dogs, I was unable to detect deterioration or even failure. And also, like a one-eyed Chihuahua, I don't have to get rid of PRP, but I need to supervise them all and not rely on them to detect precise and important things. Depth of information via two different views of a power system measurement is important in energy control system. And it's like each of us having two eyes that look at the same thing and provide slightly different information. Dual primary measurements give more information, support reasonability checks, and provide confidence, like the image on the left with a left and a right eye. The two different IEDs are instrumenting values and providing two sources of information. However, PRP replication is like the image on the right, where we have one view of the power flow, one message, and it's simply duplicated, which is like having two right eyes. The real problem with PRP is that it's designed to work if either one or the other local area network successfully gets a message through, and it doesn't detect if one of them is broken as long as the other one is working. And it will not detect a problem until both LANs fail. Now, PRP duplication comes from industries where people are present to see and fix problems, but prevents unmanned substations from detecting a problem so we can identify it early and roll a truck to fix it. We don't learn until the total failure and there's an unplanned outage. It takes a lot of work to produce an evidence-based answer of the absolute best network design, but it only takes moments and a very simple test to get these results on this slide and provide scientific truth to combat the errors and social truth about PRP. Engineering things correctly provides other advantages. Examples of the value of redundant instead of duplicate messages include data depth that supported the cyber sleuthing to break the Enigma code, and geolocating via triangulation. So Dunning points out that people are not held accountable, or sometimes unskilled, unaware, and maybe even dangerous. Power system operators are required to adhere to role-based access. They are accountable for their role and the controls they perform in the control system. I suggest that energy control system designers need to adhere to role-based accountability. They need to be accountable for what they design and the consequences of the choices they make. Device and software tools like on this laptop, require training and certification that the individuals are fit for the purpose of using the product in the specific task. Individuals are accountable to understand the underlying system, consequences of their design decisions, and they need to demonstrate that in their hands, that tool is fit for the purpose of designing and testing a mission-critical system. Every engineering code of ethics urges engineers to hold paramount the safety, health, and welfare of the public in the performance of their duties. Now, loyalty to a team and an employer are very important, but they must not override the engineer's obligation to public safety. In closing, I share some final advice from Alan McDonald after we watched the recent Netflix series about the shuttle. He told me, "You don't always have to be right, but you do have to be honest." And further, he said, "Do the right thing for the right reason at the right time with the right people, and you will have no regrets. And it will help you sleep well for the rest of your life." Alan, Anna, and I are critical of the errors that we see being made because we are optimists that things can be done better, done right, and done safely. Thank you. So that's what I had prepared. I'd be happy. I am Dave Dolezilek. Sorry, I'd be happy to take any questions.
Thank you so much, Dave. Uh, the floor is open for questions. You can unmute yourself. I muted everyone, so if you have any question, just feel free to unmute yourself and talk.
Dave, it's Rob Maher here. Thanks for the presentation.
Hey, Rob, thank you.
How did you meet Alan McDonald? Is there a story there?
Honestly, when I didn't realize he was an MSU graduate till I read his book, and then I just reached out to his email address, and he very promptly replied, and so we had an email exchange and friendship since that time. He was very friendly and helpful, and very free with his advice and experience and observations.
Thank you. And a question on the presentation. So when you talk about a mean time to failure or between failures that's incredibly long in terms of human terms, are you able to make a judgment about relative quality of two devices? If one has, let's say, 5,000 years of MTBF and another one is 3,000, is the longer one inherently better, or is either one good enough at that point?
Right. So that's a great question because it really depends on the purpose, but it is a tool used to do engineering analysis of a design for quality. So you could compare, if you're just choosing between two devices, like I said, it more or less gives you the statistical analysis of the likelihood of failure. So I would say, so typically if an IT switch is 15 times more likely to fail, that should concern you when doing a reliability assessment of an engineering design or deciding where to put it. But having said that, just because a fleet of products has a high MTBF does not mean they won't fail. And so the second part is to anticipate that failure and try to avoid it. But it's an interesting concept that's used in a lot of designs to do failure analysis. And then when you have those numbers, you can combine the products in a design all together based on how they affect each other and the outcome of the system. And then you can develop an overall awareness of the reliability of a design, which might lead you to redundant products, or you might say, this is a distribution substation. It's important, but it's not urgent that the energy flows through this station. And so for cost, schedule, and performance, you may make different choices. So it's really just a way to give reliability or quality information to make engineering design choices. So that's a great question. It also, if you find it unacceptable, it helps drive product development to improve that. And so you can't really improve things until you know whether or not they're satisfying you. measure that, and if you choose to improve it, you really need the root cause of the failure, which then leads you to know the failure rate in the field and so forth.
Thank you.
Mm-hmm. That question reminds me, there's a lot more data in the paper. I just was trying to summarize what I felt were the important takeaways, including a lot more information about engineering based on those numbers and so forth.
Great. Any question?
Actually, yes, Dave, thank you so much for the great presentation. It was very exciting, especially for me. And like here at MSU, we just started to offer power system reliability course, which
Mhm.
is greatly related to your presentation. Now, I really like that classification you made for that causes of failures, known knowns, known unknowns, and unknown unknowns. Now, when you calculate that MTBF or reliability indices based on the historical data that you have, would you say that all those three types of causes are counted for? So would you say even the unknown unknowns are counted for there?
Unfortunately, no, because physics just happens. But that points out the need to have real field data. Another way to do an MTBF, you likely know, is to do a parts analysis of what you're putting in a design and have predicted availability from the part supplier, and then populate your board and look at all the parts and how they affect each other, and do a military specification prediction of reliability. These are from the field where we capture every failure, and therefore the unknown unknowns that happen are captured. But we can't anticipate what they are, for example. But we have several fun examples where things, because they were returned, we eventually found root cause. You can go, well, I never would have anticipated that. And so you've solved one of those unknown unknowns. But you can't unless you get to root cause of every possible failure. So for us, that then drives, okay, that was really unexpected. But as soon as more than 1% of the population experiences what we formerly called an unknown unknown, that's unacceptable, and we'll take action to redesign to avoid that. And if necessary, we communicate to people, hey, you have 11 of these. We've had a very small but realistic failure of a couple of them. We'd like to repair them or replace them before they fail in service. And so we can deal with them before they fail in the power system. So by keeping track, it just drives all those possibilities. And then, yes, you can uncover unknown unknowns. They become known knowns and you move forward. But I can't say by our focus on detail has avoided all those unknown unknowns. That's the reality of physics.
Right. And that's actually very interesting. So uh, the post-incident analysis is extremely important to see
Mhm.
if that cause was something we had known before and it happened, or something that we did not know and now we know. And that
And we,
brings me to, yeah,
sorry, go ahead, please.
no, that brings me to the incident you showed in Brazil. And then you said they categorized it as not catastrophic, or it was like some low level
Right.
hazard.
The
Now,
minimum.
right, the
Because
minimum.
the energy market, or the electric power industry, only categorizes on lost load or generation. And so I'm suggesting we could do better by making people aware, yeah, that the meters won't spin, so you won't make money. But like in Texas, those outages were certainly had a lot more detrimental impact than just um, lost energy, right? Some children passed away from perhaps freezing and some other things, and a lot of damage to industry. So I'm just suggesting we should probably reconsider how we categorize failures in the energy delivery system.
So would you say it's a fair statement if we say we shouldn't just rely on engineering metrics for reliability? Maybe we need to include, social factors. We need to include, well, there are indices that will uh, include, for example, costs and so on. But the social part of the work, the problem that it might cause, that's a little bit in the shadow.
Absolutely, and that's why I use the aviation comparison, because there's a lot of comparisons between the aviation and electric delivery industry and healthcare, the three of them, because they're pretty critical to human life. I mean, everything relies on the safe and effective use of electric power. I mean, my computer here and my phone and everything that I rely on, as well as, certainly healthcare, visiting a doctor, what have you. So that's why I use that example. They correctly concern themselves with the impact to their customer, the person on the flight, as well as the crew. And I bring that example up because it then drives the appropriate engineering and maybe the appropriate demand for how reliable something has to be, all based on what are the consequences if it doesn't, right? And so, yes, I think we have the tools available to us. We just need to pay better attention to the consequences.
Right. Thank you.
I would say a couple of interesting things have also happened where when we get to root cause, we find that it's sometimes a supplier issue, and then we can work with them to do the same kind of root cause analysis, and they find that something changed in their plant, or some supplier to them had changed the quality of what they were receiving and they didn't know. And so it can cascade into being very helpful in getting to creating better designs through using data and engineering processes. I guess I would say 30 seconds we have last time. I would welcome any questions via email. Be happy to return and discuss this or another topic. I appreciate the opportunity. So I don't recall if you posted my email, but feel free to do so and people can reach
Sure.
out with questions.
Sure. Thank you so much, Dave, for the great presentation. And on behalf of IEEE Central Montana section and also the Power and Energy Group at Montana State University, I would really appreciate that kindly accept to present a talk here. And I will share your info for the folks. If they have any questions, they can directly contact you. Thank you very much. Thank you, everyone,
Thanks
and
again.
have a great rest of the day.